Welcome to the Building Science Podcast. Welcome to the Building Science Podcast.
Bringing the human factor to construction, design, and architecture. Brought to you by Positive Energy in Austin, Texas. Hey everyone, and welcome back to the Building Science Podcast. My name is Michael, and I'm your producer.
Hello, I'm Christoph Irwin. I'm your person that's going to be talking to you.
Hostess with the mostest.
I'm the hostess.
So in the last episode, we sort of introed the enclosure. And in this episode, we're going to talk about the control layers in that enclosure, specifically the water control layer.
Right. And we're going to, of course, things move hierarchically. So we're going to be moving toward talking about the control layer that deals with liquid water from this path, right? We're going to start out by reminding you that there's really only an artificial separation between the enclosure and the mechanical systems. It's all one thing. It's one tool that delivers your comfort and your health and your performance that you get in your home or your building.
And what we mean by that is we consider the enclosure a part of the HVAC.
Yeah, as mechanical geeks, definitely. We consider your enclosure is that which contains the conditioned air and that which keeps out the unconditioned air. So in that role, definitely, it's part of the mechanical system. It's a big plenum. You live in a big plenum.
Yeah, we consider them completely decoupled. They are one thing.
Yeah, and we let you have some windows and doors to come and go inside our mechanical system. So the enclosure is very important. It does the heavy lifting. We are at a place as a society where we've decided that energy and resource use are important, and in that context, the enclosure is the primary determinant of how much energy and how many resources and I don't mean resources like first cost or installed costs, things like that. I mean long-term costs of ownership as far as maintenance and repair and resource use for energy. So the enclosure does the heavy lifting. If you get it right, great, you've got it right for the long term. If you get it wrong, which is still sadly quite common, it's wrong for the long term. And in fact, it's the control layers area that has the most potential to quickly change how long our buildings last. It's not uncommon to see flashing errors and things like that. So to have an enclosure working properly, what it's doing is it's keeping the outside out and the inside in. It is not leaking. And that means a leak is considered a control layer failure. And so we're going to talk a little bit here about leaks. So when I say leaks, I don't just mean water leaks, although today we're going to be talking about water a lot. Air leaks are valid, and diffusion can leak as well, and thermal leaks can happen. And in all those cases, you have three ingredients for leaks to occur, for a control layer to fail. One, you have some sort of opening. Two, you have some sort of driving force. And three, you have something to leak. So an opening, a driving force, and something to leak. Let's go in reverse order and talk about them. So something to leak, right? So what we want to control are water, air, and heat. So any of those things represent something to leak into or out of your home. So water, rainwater, groundwater outside, water vapor in the air outside, air outside, and the particulate matter it contains, water vapor in the air outside. Bottom line is we are in this, as long as we're in the atmosphere, we are sitting in something to leak. So there's always going to be something to leak. The atmosphere is something like 5,000 trillion tons of gas molecules stuck to the surface of the planet by gravity. Hopefully it's not going anywhere.
Yeah, let's hope so.
Hopefully we're not going to follow like the Mars path here. So there's always something to leak. There are always openings in the building, right? So the most obvious example of that from a thermal perspective are windows and doors, right? So I guess air would be the doors, and any sort of glazed surface, strictly from a thermal energy separation perspective, that's a leak. Granted, it's a leak you want to have. And then the air control, there's leaks all over the place. We pepper our buildings with holes. I mean, we still have this construction methodology where we build the structure, we put on the cornice or put on the sheathing and the siding, and then we pepper it full of holes. And all those holes are potential leaks. And just to give you a number that's easy to remember, it's something to try to help give you a sense of what a hole is on a building. I'm not talking about air leak holes right now. If you can remember the number 1 million, and you can remember, then you can think about the thickness of a piece of paper. The thickness of a piece of paper is about 1 million times bigger than the diameter of a nitrogen molecule, right? An air molecule. So when we're talking about an air control layer, we're saying small holes matter, right? A 32nd of an inch gap, an air molecule moving through that is like me squeezing through the gap between Austin and Los Angeles, right? These are big holes relative to air. So driving forces. Talking right now about what moves water into your building, what moves air and vapor into your building. Those driving forces have different names, but they all have the same function, and I think this is a very important function for us to have a qualitative and almost visceral sense of how they work. So we'll start out by talking about water. We know how water moves. Water moves under the influence of gravity downhill, meaning it goes from more height to less height.
And it follows the path of least resistance.
It does, exactly. So if you can just keep that one, I mean, it's not even something to have to remember. We know water goes downhill, and the only thing to add to that is it goes from more height to less height, right? It's going from more to less. So that is a driving force. It's a huge driving force. Think of a waterfall, right? Think of a flowing river. It can move also under the influence of a pressure gradient, which is a fancy way of saying the air pressure version of downhill. You're moving from high pressure to low pressure. Specifically, what I'm talking about right now is what we call wind-driven rain. We just had a storm last Friday here in Austin. We just got obliterated. I think it was something like 14 inches of rain in a day.
It flooded the creek right next to our office so much that cars were floating away.
Yeah. I mean, it was a big rain event. So it was also accompanied by really strong gusty winds, and there had been a rash of water leaks in buildings that were previously fine for many years or more than a decade. So wind-driven rain actually can turn gravity upside down and cause water to move through cracks and move through passageways that are uphill and cause leaks that way. But if you just remember downhill from more to less, air is moving from a higher pressure to a lower pressure environment. So when someone says a pressure gradient, what they really just mean is downhill. There are also vapor pressure gradients. Those vapor pressure gradients are downhill for moisture, and that is called diffusion. So it's all the same concept, moving from more to less. The last one is a temperature gradient, the temperature version of downhill, from more heat to less heat. So there's 4 driving forces. There's gravity, there's temperature gradients, there's pressure gradients, and there's diffusion gradients. All of them operate on this same basic principle of moving downhill from high to low or more to less.
If that doesn't quite make sense yet, take a moment, rewind, and come right back here, and we'll take off from there. Got it? Good.
So expanding a little on that more to less or high to low, let's all think about a house in the summer here in Texas. You could also think about a house in New England in the winter, but we will do both, and we'll just do them quickly here. So a house in the summer here in Texas. Inside, hopefully, it's cool and dry. Outside, very likely, it's hot and humid. So from a temperature perspective, where is more, where is less, right? So from a temperature perspective, there's more heat outside and there is less heat inside. What I want you to understand is that means it is downhill for heat to flow from outside to inside. There's no mysterious driving force there. It's just more to less. It's heat flowing into your house, and it's like a bowling ball in the middle of a stretched sheet. You've made it so that all that outdoor condition, all it wants to do from all sides of your house, all 6 sides if you're on a pier and beam house, all it wants to do is come in. And so there's a constant The fancy word is temperature gradient, moving heat from outside to inside your house. So the wall thing seems to just sit there, but it's not. It's constantly assaulted by, under the influence of, this more to less force. Okay,
I feel generally assaulted by heat in the summer.
we've been assaulted, right? And now we have this dry, cool air mass inside. So we have the dry and we have the humid on the outside. So that's, diffusion gradient or a vapor pressure gradient. Those are the fancy words, but it's downhill. At that same sheet, it's downhill. So I want to say it's 24/7, but the truth is that the temperature changes over the course of the day and the humidity changes over the course of the day. But humidity-wise in Austin in the summer, it probably never the vapor pressure gradient. It's always downhill from outside to in. Now temperature might turn around briefly in the wee hours, but for the most part, it's not. Okay, let's zip up to New England, where we have the opposite case in the winter, right? So hot to cold, wet to dry, more to less. What we have is, in the winter, we have hopefully warm and relatively dry air. There's not much way around it on the inside. Well, relative to the outside, it's wet, actually, in New England in the winter. So we'll go with that. We have warm, slightly humid air because you're showering and breathing and cooking, and you have pets and plants inside your house. You have warm, relatively humid air on the inside, and you have very cold, very dry air on the outside. And the inside is constantly trying to leak to the outside. You have more to less going that direction. So it's the exact opposite.
Okay, so now that we understand the concept of gradients and how that affects vapor, air, moisture, etc., tell us about the enclosure. Tell us about the building envelope and how these control layers work, and maybe in priority order, just so everybody can wrap their minds around it.
Good. Thanks for keeping me on track here. So the control layers, well, the enclosure is an environmental separator, keeping the outside out and the inside in. And it has three functional roles. It supports the building, right? So it has that support role. It holds, your enclosure is obviously holding on your siding and holding your walls up and holding the roof up over your head. So it has a support role. It has the control role that we're talking about today. And it also has this role of protection, right? In the keeping the outside out and the inside in. It also has the role of protection of protecting the control layers themselves. And the most damaging element for the control layers is actually UV. So to think about this right, before you put the siding on your house, you're going to be able to see whatever you have there, the house wrap or the fluid applied or the peel and stick, the sheet applied coating. That layer that you can see right there, that is protected from UV by your siding or your stucco or your brick, but it is that layer that is your control layer, and it is that layer that shouldn't leak. Okay, so now in priority order, so we went through the envelope has those three roles: support, control, and protect. And in the control realm, this is really where the rubber meets the road when you think of your building as a functional assembly, not just an aesthetic assembly. So to think about, like we joked earlier on the introduction, you're not building a movie set. It needs to not just look like a building for a short time, it needs to work like a building for a long time. And we need to know that it's going to work against four primary control factors. One is what we call bulk water, which is a fancy way to say rainwater or groundwater, liquid water. So water in liquid form getting into your house is definitely a big problem, and it's definitely the highest priority, right? If your roof leaks, you're not going to be stopping and wondering if the air temperature is right, or if there's some diffusion coming in. A leak is a big problem. It's something you attend to right away, and it is a very high priority. So that's bulk water. And by the way, it obviously will leak under the influence of gravity in both the roof and the groundwater formats. So that's what we're going to be talking about today, is bulk water. The next highest priority is air leaks. Air leaks are a very big problem, a very big priority. I almost want to say that they're particularly a problem here in hot, humid climates because they can go unnoticed. In New England, if it's in the teens or 20s outside and you have an air leak, by the way, when it's most cold, often you have very gusty, windy conditions too. So when a 20-degree air leak comes into your house,
you feel it.
Yeah, you notice it. It happens. And strangely, but the reality is when 100-degree air leaks through your walls, it's not as big of a temperature difference from the inside. It quickly mixes in, and it's slightly warm, but you don't go, oh, ugh, 100-degree blast of air just came through my wall in air form, right? There's also temperature, a lot of it hemorrhaging its way through your windows if they're not shaded right. But so air is the next biggest priority. And then after air, we're back to water, but we're dealing with water in vapor form. And there's two ways there, right? So the biggest way that water in vapor form gets into your house here in Austin is it's riding along with the air. The air comes in and it's carrying many pounds of water in per day for sure, maybe even per hour. And you did hear right, pounds, right? So pints of water coming in through the air into your house. And the only way to get them out, unless you have a dedicated dehumidifier, which you should, is to run your air conditioner and to cool them out that way.
And for those of you who have used dehumidifiers before and have been able to see the effects of dehumidifying your air, you actually get the byproduct of it is actual bulk water.
Yeah.
So it's sucking it out of the air, and you could drink that water, assuming it's clean, of course. But you could put it in a cup, give it to a friend.
Yeah, it's something I almost want to go door to door is give somebody a standalone dehumidifier and just say, stick it in your living room, plug it in, and by the end of a day, an average day in an average home in Austin here, you will have easily filled that pan. It's probably a gallon, I don't know what it is, maybe, but to plug it in, sit through the course of the day, the light will come on saying pan full, carry that pan to the sink, and pour out that gallon of condensate, that gallon of water that was harvested from the air inside your home in one day. Pour it out into your sink.
Or into your plants.
Or into your plants, even better. And just feel that. It's like I say, we mediate so much of our lives through our neocortex, but we need to get past that to make real change happen. We need to feel our environment in an accurate way, and there's a lot of water, pounds of water, gallons of water inside the air in an average home. We could talk about that at a different episode. Measure it in grains. Quit talking about relative humidity. That's the pith on that one. Okay, so we had rain and groundwater, we had air leaks, we had water vapor, which comes with the air. Water vapor will also go downhill right through materials, right? And I don't mean right through tissue paper. I mean right through your siding, your rain control layer, depending on what it is, your insulation, and your sheetrock and your paint. It'll just move right through the wall. It'll even move through materials that we consider waterproof, like the vapor will now, not bulk water, but vapor is water in molecular form, and it's far smaller. It's actually smaller than air, smaller and lighter than air. So water will float on air. Water vapor will float on the air. So where was I going? Oh, I was going to talk about years ago, I used to get the newspaper delivered to me in paper form, and it would be thrown into the grass on a dew-covered morning. The sun would hit it, and if I wasn't good about picking it up soon, if I picked it up that afternoon, pull the newspaper out of that double plastic bag, probably low-density polyethylene, which we'll be talking about. Pull it out of that double plastic bag, and it's wet, right? So obviously liquid water did not leak in. It was solar-driven vapor diffusion straight through 2 layers of plastic into the newspaper. So water vapor is, I don't want to say insidious. That's not the right way to say it, but it'll get there. It'll move in. So that's the third control layer, is diffusion control, water vapor control. And the last one, strangely, as far as the codes are concerned, the last one in terms of priority from the building science perspective is thermal control. And I say strangely in terms of the codes is because that's the only one that's really regulated by the codes right now. So thermal control is insulation, and insulation is a classic control layer in the sense that it slows down the rate of temperature transfer. It is not a wall. It does not say, heat shall not move past this point. It just says heat will have trouble moving through this material and it'll slow it down.
And for those of you who are interested in the way that works and want to listen to a previous podcast that we did one on radiant heating and cooling.
Yeah.
And we talk about how deceptive the idea of cooling or heating a building actually is. So,
yeah.
Go
When we
back
talk
and listen to
about
that
thermal transport, those are the classic. We start talking about conduction, convection, and radiation. And again, we exist in an industry that is focused on conduction, and it's focused on steady state conditions, and it's focused on one-dimensional symmetry and homogeneous conditions. It's this incredibly simplified view of thermal transport. And radiation is the secret one that's really potent.
So when we talk about bulk water, what is that? Like, how do you actually control that? What are the materials involved, and how do we stay dry inside our houses?
Awesome. Yeah, so interestingly, there's a very simple and potent solution to bulk water coming from the sky.
Stop the rain?
It's your roof.
Oh.
Yeah, stop the rain. It's drought.
It's drought.
Move to somewhere where it's decided to stop raining. So no, the primary rain control layer, we'll split it into rain and ground right now. So we're going to talk about rainwater right now. The primary rain control layer is, to no one's surprise, the roof. The roof is an incredibly functional item. It protects the house from receiving the load of water falling from the sky. It protects particularly the walls and all the openings from receiving that load. Couple of points here, right? So what are the qualities of a good roof? Well, a simple roof line without lots of valleys is a highly functional roof. A sloped roof line, sloping in one or two, maybe three directions, is always downhill, is a good idea. And the next is an overhang. And believe it or not, over the course of the last few decades, all three of those have been challenged. These very basic ideas of a simple sloped overhanging roof. Now, in traditional or vernacular architecture, they were not skipped, right? In our climate here, you would have porches all the way around the house to protect the walls from rain, to keep the solar rain off, the solar load off the walls. But we as a race of beings are deciding that we want to challenge the forces of nature and to put them under our dominion. And we have decided to make roofs flat and overhangless. And that happens. I'm not going to offer any sort of aesthetic critique of it. I think there's some valid reasons to do it aesthetically. From a functional perspective, if that's happening, you really need to pay attention to how you're handling the water control layer in other areas, right? And I'm saying your walls and your flashings now. And we've seen lots and lots of problems with flat roofs and buildings with no overhangs, not because of non-well-meaning contractors and builders involved, but just because of a failure to understand the very significant role of a roof overhang and how much it was protecting the walls and how it affects wind and water flow. So wind-driven rain is a big difference. There's a big difference in terms of how water strikes a building because of wind effects when there's no overhang on the roof. I always make the comparison in my head when I think about some modern architectural hat designer coming out with the modern baseball hat, right? And we're going through the World Series right now. And this new baseball cap they've gotten rid of that old-fashioned brim. Right? So you don't want to get rid of the brim. It's not just an aesthetic thing. It's a highly functional thing. So when you get rid of the roof overhang, that's what you've done. You've gotten rid of this highly functional element. And if you want to do that, do that.
The risk.
Do that, but just know what you're doing.
The
right?
risk.
Yeah, just control the first move there. It's an old Aikido principle, and it means don't go in a dark alley alone at night, and it means don't take the overhang off your roof I think it was Shodo Oseisu in Japanese or something. So Shodo Oseisu, don't take the roof overhang off your house without knowing what it does. So recapping that, right? So we really want simple roof lines. Okay, think about all the eyebrow dormers and valleys. And there's a roof in my neighborhood shaped like a capital letter M. I mean, literally, there are two sloping, and it's like a 12-12 pitch. There are two sloping roofs flowing together. Hope I'm not there, but chances are we'll be there at some point. People seem to love complex roofs. I don't know, maybe it's a conspiracy by the roof contractors because they get more repair work that way. So you want simple roofs. You want them tilted. You really want to be friends with gravity as best you can. A flat roof is anything that's 1/4 of an inch per foot or less. And you could almost argue it's 312 or less. So you want it tilted, you want it simple, and you want it to overhang the walls. The more the better, right? So we're getting a lot of good overhangs on buildings. A lot of times it's from, here in Texas, it's from a solar shading perspective because people get it, right? It's a big comfort hit to have sun blasting through the windows. But it's also a good idea for water control, for bulk water control. So as simple and obvious as that sounds, right? So simple, tilted, and overhanging, that's the main meat of the message to remember on roofs. Now, that's not the main meat of the message to remember on water control. So we're still talking about rainwater hitting your house. Now, even if you have a roof overhang, let's say you have a 2-story house, those downstairs windows, they're still going to have water hitting them. They're still going to have water hitting the siding. Now what happens is water hits the siding, water hits the side of your house, and most of it sheds right by gravity down, out, and away down that wall. And we'll talk about out and away when we talk about groundwater. So it sheds down that wall, and it goes away and lives happily ever after, and you never worry about it. A lot of that water, I mean, maybe not a lot, I shouldn't say that. Maybe 1% of that water goes past the siding. Now, just 1%. 1% is gallons, potentially gallons of water moving past the siding. It will get in. We don't face seal. That face sealing is what we did in the 70s when we ruined a bunch of houses in the guise of weatherization. We don't caulk all around our windows. We don't caulk in between our lap siding. It will fail, it will crack, water will get in. What you do when you're paying attention to rainwater control is you acknowledge that it's going to get in and you make provisions for it to get back out. And this is an early introduction to something that you're going to hear all about in these podcasts. And it's something simple and something not done, and it's called, ventilated rain screen. Ventilated rain screen assembly. It is the king, it is the peak of the mountain solution to handling not just rainwater. I mean, you'll see it's going to help with air control and thermal control as well. But if rain gets past your siding and you have a 1/4 inch, a 1/2 inch, a 3/4 inch gap between the siding and the control layer behind it, and you have an opening at the top and the bottom of that gap, so that any water that gets back there can flow down and out of that wall assembly. Now, in a very simple way, these are not hard to build, and we'll talk about that. In a very simple format, you've delivered a very robust wall assembly. Can't forget the flashings. We build windows in walls because we have humans that need them inside the building. Whenever you put a hole through a wall, whether it's a window opening, a door opening, it's for your hose bib, it's for your air conditioning lines or electric light on the outside, that is a potential leak point, and it's one to pay attention to. And it's one that it's not a big leak and it's not a big deal if it does leak. But when you add them all up, it is a big deal. So it's also the truth that it's not expensive or hard or time consuming to take care of it in real time when you're putting that wall up. Yeah, we want the rain that hits our wall to go down, out, and away. Let's talk a little bit more about the window flashing. And I'm not going to go through window flashing. Look up window flashing details. Go to Building Science Corporation's website. They have a ton of great material on this, how-to, step-by-step, visual explanations. But a couple of key areas. One is always think down and out when you're thinking of a window. And this specifically means, like, let's start with the out. You're building a window. The first thing you do is you frame it, you put the windowsill. Please make sure your framers have a positive slope on that windowsill toward the outside. That is so simple, it is free, and it will prevent a lot of problems. It's your last layer of defense, but if water ever leaks past that window and it hits a sill that's sloped to the outside, it's going to go down the outside of the house. Now, it's not great if it's gotten to that point, but reality is that it's better than it would have been if it leaks to the inside. Yeah, what is it? People have said a leak isn't a leak if your clients never know about it.
Not a great ethos, but
no, yeah. So the next thing you do, on top of that sloped framed windowsill, you put a pan flashing, and it can be metal. Ideally, it's seamless, right? There's materials out there now that many different types. There's fluid applied, there's peel and sticks. Put a continuous pan flashing, and this just means something that goes across the bottom and up 12 inches up each side of that opening. And then, and I'm tempted to go into the window flashings, and then you follow the window flashing instructions, but you make sure that any water that was flowing down the water control layer that was on the wall above the window, you make sure that it's going to flow down in a shingle fashion, so a mechanically overlapped fashion down all the elements of the window flashing and keep going down. At the bottom of the wall, you really want something like a kick-out flashing. You want to prevent... Kick-out flashings were very common on craftsman-style homes. You want something that, as the water flows down, it gets to the bottom of the wall, that drip is moved away from the wall an inch and a half, and encounters a lip where it drips down. If it doesn't, what you'll have, and this was classic when they were using masonite a lot on construction, is that water will flow down, and by capillarity, and by surface tension, it'll move horizontally across the bottom of the siding, and then by capillarity, it'll move up the 6, 12, 18 inches up behind the back of the siding. So you're rotting your siding every time it rains, or at least tempting it to rot. So
what happens when it hits the ground?
There you go. Yeah, good. So now we follow that raindrop off our roof, or the wind-driven one. We followed it down the wall. It goes off this little kick-out flashing, hits the ground. This is so important and strangely sometimes ignored. Water flows downhill when it hits the ground. And we would like downhill to be away from the house. Mm-hmm. It's very important. We would like downhill to be, not even like, we need downhill to be away from the house. You want that water to drain down, out, and away from the house. That means everything should be sloped, right? It should be, first 6 feet, I think, are required by code. Maybe the first 4 feet. No, 10 feet. I think 10 feet have to have a positive slope. You guys can look it up. I apologize. I don't have that number held in my head. But when it hits the ground anywhere in your property, and ideally you need to pay attention to your neighbors' properties too in a downtown neighborhood, you want to make sure that groundwater is moving away from your house, not toward your house. There are quite a few pier and beam foundation homes that we've been seeing recently that have little ponds inside them, or you can see the evidence of drainage streams inside them. As it rains, the water flows from one side of the house to the other under the house. That's not a good idea. We'll talk about that when we talk about the air control layer. So what else about rain control? Simple tilted overhanging roofs. Water flows downhill, except when it doesn't. It flows uphill when there's wind-driven rain. Keeping leaves out of your valleys, very important, right? Those leaves, they seem to be just sitting there and they're nice and fluffy. There's probably dirt at the bottom. That's conducive conditions for termites and carpenter ants. You want to keep the leaves out of there. Under the roof on the valleys, you want flashing, ideally metal flashing or self-adhered underlayment. There's a lot to say. See, this moves into talking about roofing products.
Which we'll save that for another episode.
Yeah, I guess we'll save that for another episode. We're talking about the principles of control layers here. So I'll touch on it briefly that when it comes to roofing products, you really want to pay attention to the underlayment. You don't want to just have 15-pound felt up there and say, I'm done. That's, what my grandfather did. If your grandfather had access to the materials we have today for the prices we can get them today, he probably would have chose something else. So adherence tradition is a noble value, but just remember that the traditions were shopping their product selections and not ours. So pay attention to what materials you're using on the roof. If you have a relatively slow construction construction time span going on, make sure that the materials that are up there that are getting exposed to the UV are able to handle the UV for that long. Kick-out flashings on a roof flowing parallel to a wall are very important. Just Google kick-out flashing, or Google kick-out flashing rotted wall.
You can see some fine examples.
Click on images and you'll see it. Use gutters whenever ever possible. If you don't use gutters, pay extra attention to bulk water flowing on the ground. Also remember that you don't want any wood material going from the ground to your house. Water can move by capillarity directly uphill. Right? Water moves by capillarity hundreds of feet up trees, and it'll move easily tens of feet up dead trees when we use them on the connecting the ground to our house. So use a capillary break. That's a piece of plastic, a piece of metal. When water hits our house, we want it to flow. Well, it's going to flow down. It's going to flow by gravity down. We want it to flow down, out, and away from our house. So we want it to flow out of our assemblies if it does get in, and we want it to flow away from the house when it gets to the ground. So we want to drain everything. Think about draining everything. One last point here. There is this ventilated rain screen assembly, and that means there is this thing called a rain screen. Right? So this rain screen is not a product. It's a functional item. The rain screen is going to be the air gap that allows for drainage. It's going to be the drainage space, I guess, the air gap there. And it is the drainage plane on the house side of the ventilated rain screen that is made of potentially many different elements, right? It's made of whatever you've put on your wall as your water control layer. Yeah, there's no way around it. We got to talk about the three main ones, right? The three main ones are some sort of sheet good, which is the evolution of where felt went, and we'll go through the three and then we'll come back. So there's sheet goods, there's self-adhered sheets, and these are peel and sticks, like big tapes that you put on the outside of the house. And then there are fluid applied coatings. They're more new to the market, but it's not realistic to call them new anymore. So going back in order now, the sheet goods, this is probably an important feature to keep in mind. When you put on a sheet good on a house, so a lot of times felt has been replaced by these house wraps. And there's dimple wraps and drain wraps and things like that. But just speaking about the house wraps, all white house wraps are not the same. Very much so. The materials that are in them are all polymers, and poly means many, mer means small unit, so they're built of many small unit type molecules. And polyethylene is a very common one. Low density polyethylene is the lowest quality polymer that goes on the outside of a house. It is the same as landscaping fabric. So when you're putting on a house wrap, spend more and buy the good stuff if you're going that direction. And this is one of the most common faults. There are probably many, all I can assume is that there are many builders and installers that see a white house wrap and assume they're all the same. They are so not all the same. This is one where I saw them describing the low density polyethylene woven mat. Okay, so let's talk about this for a minute. So you go to the store, well, not in Austin anymore. We have a bag ban here in Austin. But if you go to the store and you get a little plastic bag at the Quickie Mart or your grocery store, that's low density polyethylene. That can be made into strips and woven into a mat. And that does happen, and it's used for landscaping fabric. And it gets buried underground and it prevents weeds from coming up. It's very cheap, and it can take on different colors. And people have decided that they would like to sell it into put it on the wall of your house market. So they've done that, and they realize, well, that's not a great idea because it leaks like crazy. So it's going to leak air, and it's going to leak water, and it's not going to work. So they've decided what we're going to do is we're going to bond to it another layer of low-density polyethylene that's non-woven, that's just clear plastic or white-colored plastic. That's just this layer of plastic. And then they're smart enough to say, well, that's actually not a good idea because I need to let the water vapor, that some water is going to get behind this material. I need to let it back out. So I need to have some way for vapor to vent it. So they mechanically perforate it. They punch it full of holes. And they punch it full of holes that are plenty big enough for liquid water to go through. So this is the one, I'm not going to read the website or quote it or anything, but I went to this website, Googling around, and they say, we have a woven low-density polyethylene mesh bonded to a mechanically perforated low-density polyethylene coating.
Oh, that sounds great, Christoph.
And I'm reading that, I'm like, why would you admit that, right? So what you want is, kind of quality order in terms of abrasion resistance, UV stability, chemical stability, and just basic strength. You want high-density polyethylene, or you want polypropylene. Both of those are higher quality materials. The gradation is low-density polyethylene is far below polypropylene, and then that is not as good as high-density polyethylene. So look at the material names. They do make a difference. And the biggest one is you want non-woven, right? You want to move away from this non-woven because the non-woven is going to be inherently, well, there probably are some exceptions, and someone might want to tell me about it, but typically non-woven is going to mean that it was bonded to another sheet that was mechanically perforated. And there's just myriad reasons why it's a bad idea. Mainly that when that technique is used, it's done in very relatively small thicknesses with relatively big holes perforated it. So you have a very flimsy water, air, and vapor control layer going on during the one time in the life of the house where you had a chance to put something good on, right? So if you're going to dress up for a, 30-year trek across country and you're going to be outside, you're going to pay attention. You're going to buy a good jacket and you're going to put it on. Do the same thing for your house. And man, oh man, is it frustrating. I'm shaking my head right now. I see high-end homes going in my neighborhood here with these crappy woven micro-perforated house wraps on them. And it's just astounding. It's like if you went to a restaurant and you found out the chef did not know the difference between a condiment and poison, mild poison, let's say. It's just astounding that it happens. Yeah, so that's my little, if I have two soapboxes, it's micro-perforated woven house wraps, and it's non-variable capacity mechanical systems. We should just stop. We should just stop doing fixed capacity systems. Okay, so after the sheet goods, we're using good quality materials properly layered on all these. After the sheet goods are the peel and sticks, or the self-adhered membranes.
It's like a giant Band-Aid.
These are like giant Band-Aids, exactly. These are sheet goods that have been bonded to an adhesive layer, and there's a huge variety of them on the market, different thicknesses, different properties. They can be vapor open, vapor closed. That's the PERM rating. We'll talk about that coming up on vapor control episode. But same principles apply. You want to buy a good quality material. Most of these are better quality materials. There's a number of manufacturers. You want to make sure they're layered properly. You want to use the primer. You want to follow the manufacturer's instructions. Ideally, you want to find a product rep that you can talk to, or even more ideally, a product rep that will come watch your first install, watch at least part of your first install, or do a mock-up with you and make sure you know how to do it. Can't stress enough to use the primers. And I want to touch on something here that's really important. I'm tempted to veer off into all the different products out there, right? The Tremco, Casella Dorkin, Dow DuPont, Carlisle, Prosoco, and these aren't written down. I'm just pulling them out of the air, remembering some. So there's myriad different manufacturers, each with their own set of products. It's just nuts to try to remember it all. I have some spreadsheets where I have it written down, but what I'm trying to do is to communicate to you guys right now that you don't have to remember it all, because that's what the internet is for. It remembers it for you. But you do need to remember the principles. You do need to shop wisely based on fundamental understanding And that'll drive good purchase decisions. So the last one after peel and stick was fluid applied. This is a game changer. It's coming on strong. I think a lot of people are going to be switching to this over time because it's a new process, but it has favorable economics when you couple the outcome into its use. So what I mean by that is gift wrapping your building from a ladder or from a scaffolding is not that easy to do. And when things are not that easy to do, they don't get done very well sometimes. So to spray a fluid applied or to roll or brush on a fluid applied control layer, and keep in mind, it's not just controlling rain that we're talking about right now, it's controlling air too and vapor. So we want to avoid these holes. Remember, driving force, opening, and something to leak. So we want to avoid the openings. And these fluid applieds, they go on thick, they dry, they're UV stable. There's just a lot of good things to say about them, a lot of good manufacturers out there, but this is getting long enough. We're talking about control layers. So I'm going to wrap up rain control. Let's see, wrap it up. So we're going to talk about the basics of a roof. The roof is a very important functional item. It's not just a decoration sitting on top of the house. You want to have a simple roof line to the extent you're willing to aesthetically. You want to have overhangs. That's a very functional item. And you want to have it tilted. You want to be friends with gravity. If you have a skylight in there, make sure it's flashed carefully. Make sure there's some way that water's shedding uphill on it. If you have chimneys around your house, make sure water flow isn't interrupted there. And then once you understand the roof, you understand the rest of it too. The roof drains down, out, and away from the house, and you want any water that lands on the ground anywhere near your house to move down, out, and away from your house. This gets into swales and French drains or sump pumps that, maybe up, out, and away is the only way you can handle things. You need a sump pump, but you want to drain the site, right? You want to drain the building. You want to drain the opening. You want to drain the assembly. You want to drain every component in that assembly. You want to drain every material. So I'm plagiarizing something I'm remembering from Building Science Corporation. You want to drain everything, right? You just want to drain the site. And final thought I want to leave you with is we're talking about rain and we're talking about groundwater. We're talking about liquid water. That and UV are the highest damage functions to your building. If your building has a problem controlling bulk water, it has a big problem for the life of that project. So this is not trivial stuff.
We didn't even touch on litigation. That's a whole other topic.
Yeah. It's funny, we talk about certain construction practices. You kind of want a lawyer in the room with you.
Well, we hope that this conversation about bulk water in its liquid form in all its manifestations in and around the house has sparked some good ideas, and we hope that you realize that there are ways to navigate the complexity, and we want to make sure that you are as informed as possible when you're going into the purchasing decisions that you have to make for your project. And stay tuned for the next episode where we will discuss air and all its wonderful complexity.
Talk to you guys later.
Thanks
Bye.
for listening.